Section 6.3 is logarithms and logarithmic functions. So logarithms are something that's completely new, so we're going to introduce them by talking about exponential functions first. So we're going to graph f of x equals 2 to the x power with a table. The table originally had -2 up to +2, but we're just going to focus on -1 up to +1. So if I substitute in -1 into my function, if I find f of -1, that'd be 2 to the -1 power. So 2 to the -1 power, if I have a negative exponent, I need to take the reciprocal of the base. So that becomes 1/2. And then when I substitute in x equals 0, 2 to the 0 power, anything to the 0 power is just 1. So 2 to the 0 power is 1. And then when I input 1 for x, 2 to the first power is just 2. So my output is just 2. And then if I want to create a table for the inverse of f of x, so the inverse of f of x equals 2 to the x, remember for inverses, their domain and range just switch. So I would have to flip-flop the columns on my table. So instead of -1, 1/2, the input 1/2 would get me an output of -1. Instead of an input of 0, output of 1, I would have an input of 1 and output of 0. Instead of 1, 2, I have an input of 2 and an output of 1. So just all of the input and output switched. It went from -1, 1/2 to 1/2 -1, 0, 1 to 1, 0, 1, 2 to 2, 1. So that's always true for all inverses. So now we can graph these. So -1, 1/2, I'm going to go left 1 up 1/2, 0, 1, just up 1, and then 1, 2, right 1, up 2. And then we can connect those points, and this is an exponential function, so like f of x equals 2 to the x is an exponential. So it's going to get really close to the x-axis, but then shoot up really quickly afterwards and start increasing faster and faster. And then for the inverse, we can graph 1/2 -1, so right half down 1, 1, 0, so right 1, and 2, 1, so right 2, up 1. And then before we connect these points, keep in mind that the inverse and the original function, they're reflections of each other over the line y equals x. So if this line is approaching this like x-axis, but it's not going to cross it, then our inverse is going to approach the y-axis, but not cross it. So we'll just get infinitely close to the y-axis right here without actually crossing it. And now you can see that our inverse and our original function are just reflections over this line y equals x. So now we're going to write the equation for g of x, which was our inverse, by switching the x and y variables. So if my function is f of x equals 2 to the x power, remember that you can find the inverse just by switching x and y. So instead of f of x equals, we could think of this as y equals 2 to the x. And then if I switch x and y, my equation becomes x equals 2 to the y power. And then usually our next step is to solve the equation back for y. And this is where logs come in. So logarithms are solving exponentials for the exponent itself. So if I want to solve this equation for y, I have to use a logarithm because that solves for the exponent of y. So the way it's written would be y equals, so solving for our exponent means that we're isolating y. And then log, or logarithm, base 2, since the base of the exponential was 2, of x. So these have the same exact meaning, it's just rewritten in a different form. So this is exponential form, this is logarithm form, so it's read y equals log base 2 of x. And the base of an exponential and the base of the log that go together, they'll always match. So 2 is our base. Y was originally the exponent of the exponential. So that's what I was saying, logs help you solve for exponents. And then x was the original kind of power. So originally with our exponential, x was equal to the base raised to the exponent, so all together that power. And then logarithms are just inverses of exponential functions. So it's a way to help us solve for the exponent, and they're inverses of each other. Kind of like how a quadratic and a square root, or an x squared and the square root of x, those are inverses. They undo each other, or they are the opposite of each other. So for example 1, it says rewrite each equation in exponential form. So you'll see with a through d, these are all logs. So if we're rewriting in exponential form, we're not actually solving for anything. This is already solved. We're just rewriting it from here to here. So this is log form, and this is exponential form. So we have to start getting familiarized with this pattern. So for the first one, log base 2 of 8 equals 3. So if I'm rewriting this in exponential form, the base of the exponential is going to match the base of the log. So if I'm setting up my exponential, I'm going to start with 2 to the what power? So since logs solve for the exponent, that means that 3, that number that's by itself, is our exponent. So this is going to be 2 to the third power equals 8. And then if we look at this little pattern just to double check it, so log base 2, this was log base b. So b became the base of the exponential, 2 became the base of the exponential. The x became the exponent of the exponential. And in this case, our x was 3, so 3 became our exponent. And then it was equal to this y value, which was 8, so equals 8. And this makes sense, like 2 to the third power is 8. If you rewrite it incorrectly, you're going to get something that doesn't make any sense, like 2 to the 8th power equals 3. So you can always check it that way as well. And then for part B, log base 7 of 1 equals 0. So the base is 7, that's going to be the base of the exponential. And then since logs solve for the exponent and it's equal to 0, 0 is going to be my exponent, so 7 to the 0 power equals 1. And that makes sense. 7 to the 0 power is equal to 1. And then for part C, log base 21 of 21 equals 1. So the base is 21, that's going to be the base of the exponential. Logs are solving for the exponent, so 1 is my exponent. So 21 to the first power is equal to 21. And these ones are kind of, well, they're not highlighted. They were highlighted, but they turned out gray because they're kind of specific. So anytime we have like log base something of 1, say we weren't, like say this wasn't solved for us, anytime we have log base any number of 1, that's going to simplify to 0 because this number becomes the 0 power, and anything to the 0 power is 1. And then over here, anytime you have the base that matches this larger number, so log base, in this case 21 of 21, that's going to be equal to 1 because anything to the first power is equal to itself. And then for part D, log base 1/5 of 5 equals -1. If we're changing it to exponential form, the base of the log is the same thing as the base of my exponential, so it's going to be 1/5 to the -1st power, since logs solve for the exponent, so my exponent is -1, equals 5. So 1/5 to the -1st power equals 5, and we know that with negative exponents we would have to flip the base over or take the reciprocal of the base, and so the reciprocal of 1/5 is 5, so that makes sense. And then for example 2, we're going to rewrite each equation in log form. So now we're going from exponential to log. So going from exponential to log solves for the exponent, so we're going to end up isolating the exponent here. So 9 squared equals 81. The base is 9. So that's going to be the base of my log. So log base 9 of, in this case, 81 equals 2. Because logs isolate the exponent, and my exponent was 2, so that's what the equation is going to be equal to. And if we compare it back up to this pattern, so in this case we're going from exponential to log, so my base b is 9, so log base b becomes log base 9, and then of y was originally what the whole exponential was equal to, so in this case 81, that's my y, so log base 9 of 81 equals the value x that was originally my exponent, so 2 in this case. So log base 9 of 81 equals 2. So it takes practice, like getting comfortable going back and forth, but the more we understand the concept, the easier it gets. So for part B, it's 5 to the third power equals 125. So if I'm rewriting it in log form, I'm going from exponential to log. The base is 5, so it's log base 5. And then I know that I'm going to end up isolating the exponent, so if I'm deciding between which value goes next, the exponent's going to end up by itself. That's the purpose of a log, is to isolate the exponent. So 125 equals 3. So log base 5, because the exponential base was 5, of 125 equals 3, because our goal with logs is to isolate the exponent. And then for part C, 16 to the 3/4 equals 8. So the base is 16, so we'll start with log base 16. And if my goal with a log is to isolate the exponent, I know that that's going to be on one side of the equal sign by itself. So the next value is going to be of 8. So log base 16 of 8 equals 3/4. And then for D, 15 to the negative second power equals 1 over 225. So the exponential's base is 15, so we'll start with log base 15. I know that with logs I'm going to solve for the exponent, so it's going to be equal to negative 2. So log base 15 of 1 over 225 is equal to negative 2. So when you're going from exponential to log form, the part of it, or the part of the equation that's going to be on its own, or it's going to be equal to, is going to be the original exponent. So like the original exponent was 2, this isolated 2. The original exponent was 3, isolated 3. 3/4, isolated 3/4, and negative 2, it isolated negative 2. And then the base is always going to match the base of the exponential. So that's probably the easiest way to start to like identifying which pieces go where. So for example 3, we're actually evaluating the logarithm. So example 1, example 2, we were just rewriting it. It was already solved for us. So we're just rewriting in a different form. But for example 3, we're actually evaluating it. So when we're evaluating it, log base 2 of 16. That's asking you 2 to the what power equals 16. What exponent is going to get me from 2 to 16? So the exponent that gets me from 2 to 16 is 4. So log base 2 of 16 equals 4. And when you're checking it, you can always rewrite it in exponential form to kind of just make sure that you're understanding it correctly. So if I were to rewrite this in exponential form, the 2 would be the base. The 4 becomes the exponent because logs are solving for the exponent, and that's equal to 16. So 2 to the 4th power equals 16. That's true, so it makes sense. So we evaluated it correctly. Part B says log base 5 of 125. So that's asking what exponent gets me from 5 to 125. So 5 to the 3rd power is 125. So log base 5 of 125 is 3. And then same thing, if you want to check it by putting it back in exponential form, you totally can. So the base is 5, that would be the base of the exponential. The log, the whole thing was equal to 3, and logs isolate the exponent. So 5 to the 3rd power equals 125. That's true, 5 cubed is 125, so we're good. So for part C, it says log base 1/3 of 27. So that's asking us 1/3 to what power is going to get us to 27. And you can always show scratch work. You can kind of write things out to help you figure it out in your head. So if I'm trying to think 1/3 to what power is going to get me to 27. Well, I know that if I want to get from, or I know that 3 cubed is 27. So 3 to the 3rd power is 27. And this is just scratch notes. You can write it down, you cannot write it down. I know that 3 to the 3rd is 127. And I know that if I want to take the reciprocal of this base 1/3, I can use a negative exponent, because a negative exponent is going to make me take the reciprocal of the base. So if I raise 1/3 to the -3rd power, well, in order to get that -3rd power to become a +3 power, I have to take the reciprocal of the base, which the reciprocal of 1/3 is 3/1. So 1/3 to the -3rd power, simplified, would be 3 to the 3rd power, which is 27. So that means the exponent that gets me from 1/3 to 27 is -3. So log base 1/3 of 27 is -3. For part D, log base 8 of 1/8. So that's asking what exponent gets you from 8 to 1/8. So if I want to go from 8 to 1/8, I'm just going from a number to its reciprocal. So if I raise 8 to the -1st power, I'm going to have to take the reciprocal of the base, which would be 1/8. This would become 1/8 to the +1 power, which is just 1/8. So the exponent that gets me from 8 to 1/8 is -1. So log base 8 of 1/8 is -1. So when you're going from like numbers to, or like a fraction to its reciprocal, or any number to its reciprocal, and you're trying to find the log of it, keep in mind that you're probably going to end up with a negative exponent, because negative exponents make you take the reciprocal of the base. So like with D, we went from a number, it's a base, to its reciprocal. We ended up with a negative exponent. For part C, we had a fraction, and then we took like a power of its reciprocal. So the reciprocal is 3, and then we still had to raise it to the 3rd power. So we ended up with a -3 exponent. For part E, so log base 100 of 10. So now we're thinking, okay, what exponent is going to get me from 100 to 10? So if I raise 100 to a whole number exponent, that's going to make 100 get larger and larger and larger. But I know that if I take the square root of 100, I'll get to 10. So the square root of 100 is 10. And I can write the square root of 100 as a rational exponent. So I can write it as 100 to the 1/2 power. So these are the same thing. 100 to the 1/2 power is also 10. So that means that the exponent that gets me from 100 to 10 is 1/2. Because if I take 100 to the 1/2 power, I get 10. And we already kind of wrote it in exponential form if you wanted to check it. This would be that same exact equation written in exponential form. The base is 100, the exponent is 1/2, and it's equal to 10. For part F, it's log base 64 of 16 equals x. So this one's kind of, it looks a little different because it says equals x, but in this case we're just solving for x. So it makes it a little bit easier sometimes when you think of it as solving like for x, because you can rewrite it in exponential form, and that can help you figure out exactly what that exponent should be. So if I were to take this equation, log base 64 of 16 equals x, and rewrite it in exponential form, the 64 would be the base. The x is the exponent because logs isolate the exponent, and then that's equal to 16. And then now I need to think, okay, 64 to what power is going to equal 16? That's a little confusing because we're getting smaller, but think on this one, we went from 100 down to 10 by taking the square root or raising it to the 1/2 power. So we're going to use the same strategy here. If I'm getting smaller, I'm gonna have to use a rational exponent. So I can think about, I know that like 64 is a perfect square. So if I were to take the square root of 64 or raise 64 to the 1/2 power, I'll get 8. But I can't raise 8 to an exponent and get 16. So that's kind of a dead end. But 64 is also a perfect cube. So I can, and this is again just kind of like scratch work, I can take the cubed root of 64 or raise 64 to the 3rd power. And if I raise, or sorry, the 1/3 power, and if I raise 64 to the 1/3 power, if I take the cubed root of it, that's 4, because 4 times 4 is 16, and then times 1 more 4 is 64. So then now I know that to get from, I've taken the cubed root of 64 to get 4, and then if I want to get from 4 to 16, I can square 4, and that'll give me 16. So that means if I have to take 64, raise it to the 1/3 power first to get 4, and then raise that 4 to the 2nd power to get to 16, I would do 64 to the 1/3 power squared. So this is just 64 to the 1/3, that's 4, and then 4 squared gets me to 16. And then now we can start to see like what the total exponent should be, because it should be like one simplified combined fraction if it's a fraction. So 64 to the 1/3 times, or sorry, 64 to the 1/3 raised to the 2nd power. I know when I have a power to a power, I multiply those exponents. So if I were to multiply 1/3 times 2, I would get 2/3. So that means that 64 to the 2/3 is equal to 16. So that means that x is equal to 2/3. So just to kind of talk through that like one different way. So log base 64 of 16 equals x. So that's saying that x is the exponent that gets us from 64 to 16. And I know that with rational exponents, when I change it to radical, the denominator ends up being the root or the index, and the numerator ends up being the exponent. So if I were to take 64 and raise it to the 2/3 power, I would take the cubed root, which is 4, and then I would square it. So the cubed root of 64 is 4, and then 4 squared is 16. So that matches up. So x is equal to 2/3 is our final answer for that one. And then just one more time, that means we're taking, to get from 64 to 16, we take the cubed root and then square it. So the cubed root is 4, square the 4 to get to 16. So the next thing we're going to talk about is common logs and natural logs. So those are just like specific types of logs. So a common log is just any logarithm with a base of 10. And then we write that without the base actually showing. So a common log is log base 10, we'll say, of x, so of any number. If you see log x where there's no base there, there's an assumed 10. So anytime you don't see a base, it's a log with a base of 10. And then for a natural log is a log with a base of e. So we talked about e in section 6.2. So any logarithm with a base of e, so log base e of x, we write as ln x. So you can't see the actual base, just ln x means log base e of x, and it's called a natural logarithm. So using inverse properties with logarithms is like kind of fun, but by definition of logarithm, it follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b of x. So that was what we were talking about like on the very first page, where we graphed y equals, or f of x equals 2 to the x power. And then the inverse of that was our log, y equals log base 2 of x. So we kind of showed that, and this is just now a general statement. And we know that with inverses, like if I find the composition of inverses, so like g of f of x or f of g of x, then everything should cancel out if they're inverses and we'd just be left with x. So that works for logs as well. So if g of x is log base b of x and f of x is b to the x power, g of f of x means that I'm taking f and substituting it into g where x is. So log base b of, instead of x, it's b to the x power. And with inverses, everything cancels out and we're just left with x. So the log base b and the exponential with the base b, those cancel out and we're just left with that exponent. And then for f of g of x, we're taking g and substituting it into f where x is. So instead of b to the x power, it becomes b to the log base b of x power. And then same thing, if they're inverses, everything is going to cancel out besides x. So the exponential with the base of b and the log with the base of b undo each other, and we're just left with that x. So you can use that in order to simplify some log expressions. So for example 5, simplify using inverse properties. So for a, I have 10 to the log 18. So remember, if you don't see a base on the log, it's an assumed base 10. So then the exponential with the base of the 10 and the log with the base of 10 undo each other, and we're just left with 18. So our simplified answer is just 18. And then for b, log base 4 of 16 to the x power. So this one, the base of the log doesn't match the base of the exponential. The base of the log is 4 and the base of the exponential is 16. But 16 we can rewrite as a power of 4, so that's what we're going to do to use the inverse properties. So log base 4 is going to stay the same for now. And then 16, I'm going to replace with 4 squared. So I'm not changing the value, I'm just replacing it with 4 squared. It's still being raised to the x power. So then 4 squared to the x power, I can simplify that because I have a power to a power, so I can multiply them. So log base 4 of 4 squared to the x, so I multiply 2 times the x, and that becomes 4 to the 2x power. So then now the base of the log matches the base of the exponential, so those undo each other. The log base 4 and the exponential with the base of 4 undo each other, and I'm just left with 2x. And then for c, 8 raised to the log base 8 of x, so the exponential with the base of 8 and the log with the base of 8 undo each other, and I'm just left with x. And then for d, log base 7 of 7 to the negative 3x power. So I have a log with the base of 7 and an exponential with the base of 7, so those undo each other, and I'm just left with the negative 3x. And then for example 6, it says find the inverse of each function. So finding the inverse, it works the same way as that we've learned before, where we would replace f of x with y and then switch x and y and solve the equation back for y. So a is f of x equals 11 to the x power, so I'm going to replace f of x with y. So y equals 11 to the x power, and then I have to switch x and y. So when I switch x and y, it becomes x equals 11 to the y power, and then I want to solve the equation back for y. So in order to do that, I have to use a log. So this is just changing it from exponential form to log form. So back to the last page, if I have that log base b of y is equal to x and b to the x power is equal to y. So I can use this same pattern to rearrange it and isolate y, because when I have an exponential and I want to isolate the exponent, I need to use logs. So the base of the exponential is 11, so the base of my log is also going to be 11. I'm using a log to isolate y, so it's going to be, the whole thing is going to be equal to y. So log base 11 of x is equal to y. So my b, that was originally 11. My x, that was originally y. I know these are flip-flops, so it's a little weird. And then my y was originally x. So I end up with log base b, so log base 11 of x equals y. I know this is a little weird because those are like flip-flop from the pattern, but just kind of keep in mind like the placement of each. And then for b, y equals ln, or natural log of x plus 6. So we'll have to switch x and y to find the inverse. So x equals ln y plus 6. And then I want to rewrite this in exponential form. I know that it gets like, it's kind of weird getting used to ln at first. So if you need to, you can rewrite it as like log base e. That might help you see it a little bit differently. So x equals, instead of ln, log base e of y plus 6. And you would never do this in your final answer, but it can help you kind of see how to rearrange from log form back to exponential. So if we want to solve for y, I have to get rid of this log. So if I want to isolate y, I need to get rid of the log. In order to get rid of the log, I can go from log form back to exponential. So the base of my exponential is e. And then it's solved, it's equal to x. So that means that x is my exponent. So e to the x power is equal to y plus 6. Just following this pattern to change from log to exponential. The base of the log becomes the base of the exponential. What it's equal to, I'm solving with a log, isolates the exponent. So x becomes my exponent, and it's equal to y plus 6. And then the last thing we need to do is just subtract 6 over to isolate y. So y equals e to the x power minus 6. And then for part C, y equals 3 to the x plus 5. So we'll switch x and y like before. So instead of y equals, it'll become x equals 3 to the y power plus 5. So now y is like my exponent. So if I want to solve for the exponent, I need to use a log. But you really want to isolate this exponential first. So I'm going to subtract the 5 over first, and then I'll be able to use a logarithm to isolate the exponent. So x minus 5 is equal to 3y. And then if I want to isolate this exponent, I can just rewrite it in log form. So it was log base 3, since the exponential is, or the base of the exponential is 3. I'm using a log to isolate y, so that's what it's going to be like equal to after. So log base 3 of x minus 5 is equal to y. Same thing as before, just using this pattern to go from an exponential to a log in order to isolate the exponent, the y. So y is equal to log base 3 of x minus 5. And then the last part of this section, we're just going to introduce graphing log functions. So we graph log functions pretty similar to exponentials, or we just like use knowledge of graphing exponentials in order to graph log functions. So just knowing that like logs and exponentials are inverses are going to help us pick like the x values for our table. So if we go down to example 7, 7a says f of x equals log base 7 of x, and we're going to graph it. So with the table, we'll use x and f of x. So when we first learned, or when we graphed the exponential function at the beginning of this section, we just, for x, we picked -1, 0, and 1. And when we picked -1, we got the reciprocal of the base. So our base was 2. So when we picked -1, we got 1/2. When we picked 0, we got 1, and when we picked 1 for x, we just got the base back. So 2 to the first power just kept that 2 base the same. And then when we flipped the inverse, or the input and output for the inverses table, we just flipped negative 1, 1/2 became 1/2 negative 1, 0, 1 became 1, 0, and then 1, 2 became 2, 1. And this was the graph for this log. This was the table for this log, the inverse. So if I want to create a table, my x values should be, in this case, the base is 2, so it should be the reciprocal of the base, 1 and 2, every single time. The reciprocal of the base, or sorry, not 2, but the reciprocal of the base, 1, and then the base every single time. So these numbers, the 1/2 and 2, will change depending on what the base is. It'll always be 1 in the middle. So reciprocal of the base, 1, and then the base. So for 7a, if I want to start with the reciprocal of the base, the reciprocal of 7 is 1/7. And then the next value is 1, and then the next value should be the base, so 7. All the time. And then when x equals when x equals 1/7, so this becomes log base 7 of 1/7. So that's asking you what exponent gets from 7 to 1/7. Well, to get from a base to its reciprocal, I have to use a -1 exponent. And then for log base 7 of 1, that's asking what exponent gets you from 7 to 1. So if you want to go from any base to a power of 1, my exponent has to be 0. So 7 to the 0 power equals 1. And then for log base 7 of 7, it's asking what exponent gets you from 7 to 7. Well, that's 1. So you'll start to notice that as long as you pick the reciprocal of the base, 1, and the base, you're always going to get -1, 0, and 1 out. Depending on, it might be a little different if you have some like vertical and horizontal translations, but for like kind of our parent function, that's always what you'll get out. So now we can graph it 1/7, -1, so right about a 1/7 and then down 1. Just graph it as accurately as you can, and then 1, 0, and then 7, 1. And then with this graph, it's going to get infinitely close to the y-axis, but it's never going to cross it. And then the line will start to get really flat up here. So for the domain, because we're going to get infinitely close to the y-axis without actually ever crossing it, the domain has to be non-negative numbers for x, because it's never going to go into the negative part of the graph. So my domain is x is greater than or equal to 0. Or sorry, scratch that. It's just greater than. Let me go back and explain that a little bit better. So the graph is never going to cross or touch. It's going to get infinitely close to the y-axis, so it's going to get, x values are going to get infinitely close to 0, but they're never going to be 0, and they're never going to be negative. So x is just greater than 0, not greater than or equal to, because it'll never actually touch the y-axis. And then for the range, it's going to go forever in the negative y direction. It's also going to go forever and increase forever in the positive y direction. It definitely slows down a lot, but this line will never become like completely horizontal, so y will always steadily increase. So the range is y is all real numbers. And then for the asymptote, because this line is never going to cross the like y-axis, there's an asymptote there, kind of like with rational functions. So it's never going to cross this y-axis line. The y-axis is the line x equals 0. And these two are always going to correspond. So if the domain is x is greater than 0, the asymptote is x is equal to 0. If the domain changes, the asymptote changes. And then for the x-intercept, we can see on our graph our x-intercept is 1, 0. The y-intercept, there's not going to be any, because it's never going to cross the y-axis, so it's not going to touch it. There's going to be no y-intercept. And then for the next example, the last one, part B, it says y is equal to log base 1/4 of x. So we're going to do the same thing, make a table, so x and y. And then for the x values on my table, I'm going to use the reciprocal of the base, 1, and the base. So my base is 1/4, The reciprocal of that is 4. Then 1, and then my base is 1/4, so my next value is 1/4. So it's always going to be the base, or sorry, the reciprocal of the base it's always 1, and then always the base every time you go to graph these. So when I substitute in 4, so log base 1/4 of 4, I have to think 1/4 to what power gets me to 4. So 1/4, the negative first power gets me to 4, because it would require me to take the reciprocal of 1/4, which is 4. And then 1/4, when I input x equals 1, 1/4 to what power equals 1? Well, 1/4 to the 0 power equals 1. And then when x is 1/4, log base 1/4 of 1/4, that's asking what exponent gets you from 1/4 to 1/4, and 1/4 to the first power is 1/4. So it's the same thing as over here where we picked reciprocal of the base, we got -1 out, we picked 1, we got 0 out, we picked the base, we got 1 out. So that'll always be true. And then there may be some horizontal vertical translations along the way, but those are easy to adjust once you kind of get these 3 values. So if we graph it, 4, -1, 1, 0, and 1/4, 1. And then you can see this one's kind of like a reflection, but it's still going to get infinitely close to the y-axis without ever actually crossing it. So for my domain, what x values are possible, this line is going to get infinitely close right here, but it's never going to cross it. So x is always a positive value. It'll never be in the negative region. So x is greater than 0. My range, we're going to increase forever in the y direction. We're going to decrease forever in the y direction. Even if it starts to decrease slower, it's okay. My range is all real numbers. My asymptote, my domain didn't change, so my asymptote is still at x equals 0 because it's never going to touch this x equals 0 line. My x-intercept I can see is 1, 0. And then my y-intercept, if I'm going to get infinitely close to the y-axis but never actually cross it, then I don't have a y-intercept. Okay, so the biggest thing with graphing these is, especially when we are just starting and there's not a whole lot of transformations, for your x values, you're just picking the reciprocal of the base, and you'll always get out -1, 1, and you'll always get out 0, and the base, and you'll always get out 1 whenever you're creating a table for a log function.